The Commodore 64 computer, launched 40 years ago in January of 1982, went on to change history by selling over 17 million units, making it still the best-selling home computer ever. And in this limited series, inspired by the fantastic Canadian CTV show How It's Made, we started with archived factory footage courtesy of Commodore.ca, but which unfortunately, although the only known version, is of quite low quality.
Auch hier wird wieder getestet.
So we translated it from German with a few updates and restored it using machine learning to take an unprecedented look at the Commodore 64 and how it was made. Without a computer, there is no space travel, no global communication, no home entertainment. But back in the 1940s, to achieve just a fraction of the performance of a home computer today, machines like the Colossus Mark I required large rooms, vast amounts of money and electricity, and multiple highly trained operators. A better way was the vision of many, including Polish-American businessman and Holocaust survivor Jack Trammell, who in the 1950s and 60s was dreaming of that future when he began producing electronic calculators and typewriters. And just 2 decades later, here in 1982, mankind is finally on the threshold of that fantastic future where young people stand at the cusp from the comfort of their homes and where the key to the world of tomorrow lies in devices like the Commodore 64 computer, so cheap it can be afforded by millions. And it's all happened because of people like Trammell, but also owing to the transistor, a tiny electronic switch or amplifier comparable to the neurons in our brains. When contrasted with the electron tubes of the Colossus that it's made obsolete, a transistor uses far less power, works more quickly, and is much cheaper. By combining several transistors on a single silicone plate, giving millions of transistors and operations for just one of these tiny pieces, it's possible to shrink devices considerably. And this unimaginable precision is only possible at such cheap prices due to companies like Commodore using their own chip technology, a strategy companies of the future like Apple may take decades to catch on to, perhaps with a switch from Intel to Apple Silicon, for example. But back here in 1982, it means that Commodore computers can be designed largely independent of the global market, allowing tailor-made chips with the highest degree of integration. And to discover exactly how this design and manufacturing takes place, the German factory in Braunschweig, where the Commodore 64 and other machines were assembled, will be our last stop along the way. The Commodore is, like us, a product of our cosmos, made on Earth, a triumph of human spirit. But when the computer heart beats for the first time, it has come on a long journey, a journey that begins at our first stop along the way, not in Germany, but in the sea, where all life arose from. And where the continents and oceans meet lies the source material for our computer silicon. Because silicon oxide is nothing more than sand, the base material for electronic components. It's the second most common element on Earth. You can find it in sandstone, quartz, and rock crystal. But computer silicon is only suitable as a building material if it contains absolutely no impurities. In fact, for every 10 billion atoms, at most 1 foreign atom may be present. From the sand crystals, chunks of silicone rods are formed, and it's these rods that the circular wafer-thin slices are sawn off. Silicon wafers. The computers help themselves to a certain extent, because the construction of thousands of circuits on an area of just a few square millimeters is no longer possible with a paper, ruler, and pencil. A C64-style microelectronic circuit, you may know it better as a chip, contains, for example, 64,000 cells with many individual transistors, each one drawn into CAD or computer-aided design software. Here at our second stop along the way, Commodore's Westchester facility near Philadelphia. An engineer enters his design into the computer with an electronic pen moved on a tablet. By tapping on the drawing board cell by cell, every step can be mirrored on the screen. And so it's computers themselves that help the engineers find their way through this maze of conductors, transistors, and other components. Also needing reduction to microscopic size are the chip blueprints. But which pen could transfer structures that are more than 10 times smaller than a human hair onto the silicon wafers? After all, these giant plans with their hundreds of thousands of details later appear on a chip only a few square millimeters in size. Well, here at our third stop, another computer creates a tiny production mask for the chips. Next, a magnetic tape records those digitized chip construction plans for safekeeping and future playback further along in the process. We'll come back to that in a moment. But much of this top-secret manufacturing takes place in a closely guarded security area. Officers like this one patrol the area to ensure no competitors may sneak on board and steal the trade secrets. But as we, as very special guests, peer into this secret alchemist's kitchen, we see the chip-building machine from which the legendary 6502 microprocessor, the heart of the Commodore 64, is made. Here in 1982, this is one of the most widely used computer processors in the world, and so 3 shifts of workers beaver away feverishly around the clock to produce this light of the electronics world. Our magnetic tape has meanwhile landed at the other end of the hermetically sealed, humidity-controlled factory floor, where conditions exceed those of a spaceship or an operating theater. Our electronic space travelers here must therefore wear a protective suit and overshoes, known as booties. The reason is that in the microscopic structure of the chips, a speck of dust is like a meteorite and would have devastating effects, destroying the fine electronic circuit's structure. But with the room's conditions perfect, how do the blueprints get from the magnetic tape onto the silicone wafers and form circuits? Well, like with a photograph onto paper, the first step takes place in the photo darkroom, where yellow light protects the source material. Here, a worker exposes the silicone wafer to a photo mask before giving it a chemical treatment to burn that chip design, visible through the mask, onto the wafer, whilst leaving the masked area untouched. And since the production of this chip takes place in several steps, separate photo masks are required for each step, creating a photograph that is about 10 times larger than the area of the chip. You could think of this as the initial passport photo of the chip. A worker checks the photo transfer under the microscope to confirm everything is correct. Now, under blue light, 10 times smaller copies are made by computer-controlled machines, creating a new photo mask for the production of many chips on a single silicon disk. Computer test programs compare the original and the copy. Next, an examiner uses their instincts to analyze the circuit as if it were a little city and they were looking for damaged or collapsed houses. The wafers that will become our Commodore 64 processor are now covered with a light-sensitive oxide layer. Chemicals are then added which etch away and remove the exposed, unprotected part of that image, leaving microscopic finished patterns that we may know as circuits. Workers repeat this process over and over with the different designs for the different chips that will make our Commodore 64, until all the layers on the chip are sandwiched in. Engineers finally check that the circuit's interaction results in the correct electronic function. At midnight, the third shift of engineers take over and place the oxidized wafer in a diffusion furnace. Here, the wafers are heated and subjected to a flow of gaseous molecules known as a vapor phase. This phase, known as doping, fixes the molecules inside the wafer, altering the molecular structure of the silicone to make it most suitable for use in chips. After 3 hours, the wafers come out of the oven, sporting their hundreds of thousands of tiny transistors or electronic switches printed by the photomasks and all made atomically suitable by the diffusion furnace. Next, it's time for ion implantation. This process embeds fast-moving particles in the wafer at specific locations, depths, and concentrations, permanently changing the semiconductor's electrical qualities by selectively creating an abundance of electrons or electron vacancies at specific locations. Layer by layer, an army of workers use other computers to test the chips. Any chips that fail the quality check are marked and set aside. After several chemical treatments, the wafers arrive at a sort of electronic acupuncture device, itself covered with a black cloth to again protect the wafers from certain wavelengths of light. This machine's needles in this case are in fact test points which, like the probes of a multimeter, automatically check the electronic function and circuit continuity of the chip. Now, a worker adjusts and aligns the edges of the wafers so a precision saw can cut the chessboard-like chip pattern exactly. Then, all harmful dirt particles are scrubbed away. And now the final separation into individual chips takes place, with scrap either thrown away or recycled for future use. The clothing for the chips is waiting here and comprises of either a ceramic or plastic housing with connection pins on the outside and contact points for the chip itself inside. The tiny chip inside the chip is glued into the middle, truly a job for steady hands. The chip clothing seamstress arranges the connection between the chip and the outside world in a bonder, where a wafer-thin gold thread is laid from connection point to connection point. Once all the wires are in place, the stage is set for a final visual inspection and a last test before the chip is locked away into its eternal darkness. Ooh. Closing the housing with the cover plate is the crowning glory of a long chain of steps that every chip that makes up the Commodore 64 must go through, in the hope that those chips will last perhaps 40 years or more. And to help assembly workers and future service centers tell them apart, every chip has its name and part number branded with a stamp. Perhaps in future decades, everyday hobbyists might even use the part numbers when repairing these illustrious machines. And just like humans have varying personalities, computer chips also differ from one another. Some are fast, others consume less energy, and so on. That's the reason why they're subjected to another character test in these machines and sorted according to certain criteria and characteristics before being packed. And now the great journey begins to the chip's final destinations, Commodore 64 production facilities in Asia and this one in Braunschweig, Germany. In these facilities, the chips and other components such as ports for connecting accessories, capacitors for storing energy, and resistors for adjusting the voltage are assembled onto the computer's motherboard, known as a PCB. You can even have your own Commodore 64 PCBs manufactured in this way today from the comfort of your home using PCBWay. Yes, they really do manufacture new Commodore 64 PCBs for customers even today. Because as we all know, PCB stands for Packed at Commodore Braunschweig. Can we check that with the producers before publishing this?
Yeah, of course.
Okay.
Cool.
Thanks.
You're welcome.
In the human body, organs like the heart, kidneys, or liver have an important task to fulfill, and the way they're connected via arteries and the nervous system is crucial. And just like with the human body, the C64's PCB only works if all the components communicate effectively with each other via the PCB's version of a nervous system known as its traces, the small copper-colored pathways you see on the computer's motherboard. Along with the 6502 processor chip, other key chips that make their way to be soldered onto the PCB and to communicate via the traces include the VIC-II graphics chip, the SID or Sound Interface Device, and various other chips that help the Commodore 64 communicate with the outside world via its ports, keyboard, or joysticks. Several smaller chips known as RAM or Random Access Memory are also needed to give the computer the 64 kilobytes of memory that gave the C64 its name. Here at the German factory, a new shipment of PCBs has just arrived from another Commodore factory in Asia for final assembly. Much of its nervous system has already been assembled, but before its brain can start to think, it has to undergo a rigorous physical. Skilled workers check all of its sensors are working properly, including its incredible 16-color graphics display and magical 3-channel sound. Here, a software testing program provides information to the engineer. Next, the graphics output is trimmed and adjusted to perfection. Shown here in the Asia factory, workers add anti-interference RF shielding to the motherboard to comply with the strict FCC regulations present here in 1982. From there, it's time for the computer's brain to receive its body. Let's accompany this Commodore 64 along its own assembly line. Here, a worker conducts a soak test, a sort of endurance test of several Commodore 64s lined up on long shelves. Any machines that fail the test are taken away to be brought up to scratch, but even those who pass the test are not out of the woods yet. Here, the Commodore 64 undergoes a final battery of checks to make sure they can speak the language of the end user, in this case, Commodore Basic 2.0. The machines go into a final assembly, testing and packaging production line, along with other Commodore machines, such as the still popular Commodore PET, seen here, with its components slowly filling its housing. Here too, tests are carried out again on all the machines, until the quality leaves nothing to be desired. And finally, the long production path, from grain of sand to wafer to chip, and from the USA to Asia and finally Europe, is done. The next and final journey is really the assembled Commodore 64's maiden voyage, equipped with all of its necessary test certificates and packaged safely in its box, ready for the consumer to open, perhaps under a Christmas tree one year, in an office, or even on a YouTube channel in the distant future, and where adults can work and program and children can learn and play, not with sand this time, but with a state-of-the-art computer made from it. Each new Commodore 64 can be proud to have traveled so far and through so many steps to make it what it is, and its new owner will no doubt be equally proud to own one. Thank you for watching, and for more like this, subscribe and support below, and cheerio.